the first sign would be small. Through a telescope, a single star would appear to split in two. Perhaps it would be dismissed as a mistake, an oddity caused by a problem with the lens. But then a few nights later, telescopes across the globe would spy the same thing. Detectors around the world would notice increased levels of cosmic, UV, and gamma rays. Something energetic would be detected happening in the nearby universe. Then would come the rumbling. To begin with, it would be subtle, noticed only by gravitational wave detectors, strange ripples in space fitting no known template, an invisible approaching threat. But in time, we would see it, stretching from one horizon to the other. As if it cut the universe in two, it would pulse with exotic energies. When it whipsawed onto itself, it would create an explosion brighter than a supernova. And indeed, by the time it became visible to the naked eye, it would already be too late. The universe holds close its dark secrets. Beyond the boundaries of the known and familiar, past the protection of the sun and the circling embrace of the Milky Way, lie relics of its ancient past, remnants of the Big Bang itself. There are defects in the cosmos, and they have been here a long, long time. They were there in epochs of fire and unification at the beginning of everything, the long eras of splintering and fracturing, the chaos and violence before the universe as we know it took its final shape. They appear in our theories. We give them names, we assign them properties, we ask how they might survive to the present day, how we might detect them through a subtle signature in this or that survey. We tell ourselves we are safe. But perhaps we are wrong. In February 2011, Robonaut 2 became the first humanoid robot in space. Initially designed as a prototype to be used on Earth, mission managers chose to send it to the International Space Station after being impressed with its capability. It could be controlled remotely, either by crew members aboard the space station or even back on Earth, and was invaluable to engineers in demonstrating how dexterous robots function in space. Sometimes it's useful to be able to control something remotely, even from the other side of the world. And if you're looking to remotely control your computer for personal or business reasons, AnyDesk can help. AnyDesk is a lightning-fast remote access tool that makes it feel as if you're sitting right in front of the remote machine. Indeed, we find it especially useful for video editing. Our editors can access their high-performance desktops back at home on the go, even with low-spec laptops. This allows us to take cheaper, older, or more portable machines to the coffee shop or gym without losing any productivity. AnyDesk is available across all major platforms, is backwards compatible with older operating systems, and has 99.98% uptime reliability, so you can depend on being able to use it when you need to. And what's more, personal use is totally free, with tailored plans for team and business environments. So head to anydesk.com to try this premium remote access tool free of charge. We live in a broken universe, and in 1983, physicists revealed a more perfect one. The laboratory was called Underground Area 1. It sat outside the main detection chambers of CERN, the collection of massive particle colliders situated at the border of France and Switzerland. The main detector consisted of a series of cylinders almost 6 meters long and over 2 meters wide, filled with ultra-pure neutral argon and ethane gases. A complex zigzagging of 17,000 wires and over 6,000 sensors tracked the three-dimensional movement of any charged particles as they raced through the chamber. After years of development, the team at UA1 had hacked together a new kind of collider, one that combined protons and antiprotons together at nearly the speed of light. With the machine in operation, the particles raced around kilometers of circular track, accelerating to higher energies with each pass, coming within centimeters of each other. Finally, at the last moment, right at the very limits that the accelerators could achieve before their beams of particles drifted off course, the engineers initiated a carefully orchestrated sequence of events that brought the twin beams into collision precisely within the UA-1 chamber. And for the barest fraction of a second, when the energies peaked and the collision ignited to its maximum intensity, a pure, infant universe was born. This new universe was unbroken, symmetric. Strange particles sprung into existence, the wires and detectors of the chamber briefly registering their exotic presence before they flashed away. But this was no portal into another dimension. It was a window into our past. Few people anticipated what would happen on that fateful day in 1983. Some of them, like Peter Higgs, are well known today with their names attached to Nobel Prizes and international recognition. But some stayed out of the limelight, content to do their work regardless of the promise of fame. By all accounts, Sir Thomas Kibble was the gentleman's gentleman and the scientist's scientist. He was kind, gregarious, and dignified. He delighted in his work, in the camaraderie of his peers, and his ventures into the frontiers of physics. Indeed, in 2013, when Peter Higgs was awarded the Nobel Prize, he expressed regret that Kibble was not joining him. And yet when asked his own opinion, Kibble simply shrugged. He was happy with what he had accomplished. He didn't need a gold medal to reap his rewards. But what was it that he had found? What was it that was confirmed in the fires of CERN in 1983? The theory of the Big Bang tells us that the universe was smaller, hotter, and denser in the past. Billions of years ago, the entire observable universe had a temperature of over 1,000,000,000 degrees and was compressed into a volume no bigger than a peach. And Peter Higgs, Tom Kibble, and others discovered that at those insane energies, what we call the forces of nature take on an entirely different form. There are 4 fundamental forces that control everything within the universe: gravity, electromagnetism, and the strong and weak nuclear forces which operate at atomic scales. At least, there are usually 4. For at high enough energies, we know that 2 of these disparate forces merge together into a single unified whole. At extreme enough energy scales, there are no longer 4 forces of nature, there are only 3. Gravity, the strong force, and the electro-weak force. This is a symmetry of nature, exposed only at incredibly high energies. The electromagnetic and weak forces become 2 sides of the same coin, the same way we view electricity and magnetism as 2 sides of electromagnetism. But this symmetry is broken in the everyday cosmos, with some mechanism driving a wedge between them, making them appear and act as completely different forces. And it was Higgs, Kibble, and others who figured out how to create that wedge through the introduction of a new particle field, now named after Higgs, the Higgs boson. At high enough energies, the Higgs boson is in an unstable but symmetric state, like a pencil balanced on its tip. But at low energies, the Higgs boson devolves, collapsing into a more stable equilibrium. However, like a pencil falling over, that equilibrium is no longer symmetric. It is the broken symmetry of the Higgs that separates the weak from the electromagnetic force, enabling their wildly different properties. And there are only 2 places where the more perfect union of the forces is restored. One is in the heart of our most powerful particle colliders, just as scientists at CERN achieved in 1983, and the second is in the earliest moments of the Big Bang. But for Kibble, that was just the beginning. What if this process of symmetry breaking was not perfect? And this is when he became interested in something called phase transitions. Phase transitions occur when a substance transforms itself due to changes in temperature or pressure or density. Freezing, melting, evaporating, the cycles of water on our planet, from the dew glistening in the morning sun to the ice clinking in your glass, are all examples of phase transitions of water from one form to another. But it's not only gases, liquids and solids. As another example, within an extremely dense kind of star called a neutron star, some atoms are crushed so tightly together that they transition into a whole new form of matter, dubbed nuclear pasta by physicists. Kibble, however, wasn't interested in your run-of-the-mill phase transition. He was interested in the kind where symmetries break. If you let a pencil fall from its tip 1,000 times, you'll end up with 1,000 different results. Each one is equally in equilibrium, yet utterly unique. And yet at the same time, even though the unique pencil directions are all different, it doesn't really matter. The pencil is lying on the table. The physics of the situation remains unchanged. And so when we turn on a particle collider and achieve the unification of the forces, the symmetries between the weak and electromagnetic forces manifest. The two forces become one. But when we turn it off, the Higgs boson falls back into a low energy state, one of an infinite number that it could choose. Yet it doesn't matter which one. Like the pencil on the table, what matters is the asymmetry that breaks the unification of forces, not the actual choice of low energy state. And so when the universe cooled from the hot Big Bang within the first nanosecond of existence, the Higgs boson chose a particular low energy state across the entire universe. Or maybe it didn't. For as Kibble worked his way through the maths of the phase transitions of the early universe, he realized that the breaking of the fundamental symmetries didn't necessarily have to proceed in a smooth, orderly fashion, with the entire cosmos acting in synchronicity as it cooled off. Some regions may have stayed hotter a little longer than others. Some may have experienced random quantum fluctuations in one direction or another. No matter what, the Higgs boson collapsed, that was certain, but it could have collapsed in different ways and at different times as the universe evolved. And so Kibble dug a little bit more. When you freeze a bit of liquid water, its molecules fall out of a symmetrical state into an asymmetrical one. A drop of liquid water looks the same, microscopically at least, no matter how you look at it. But an ice cube is different. The water molecules lock up with each other in regular geometric patterns, a crystal lattice that transforms the liquid into a solid. But different parts of the water will freeze out at different times. The geometric patterns the molecules form may line up in different directions, like one regiment of soldiers coming to attention facing one direction and another regiment facing somewhere else. Within each region, everything is as it should be. The water is in its lowest energy state, the symmetries of liquid have been broken, and your interaction with the ice cube, say for example, putting it in your drink, stays the same. But where these differing regions meet, a fault line appears, a defect. Kibble couldn't help himself. He knew of the analogy of water crystallizing into ice and applied the same mathematical techniques to explore what happened in the early universe. What he found was a monster. One more ancient than the galaxies and stars, one born in the very fires of creation. When the universe cooled from its pristine, symmetric state, the Higgs boson fell from grace. But perhaps in one region of the universe, it fell to one particular low-energy state, and in another region, another low-energy state, and in yet another low-energy state, and on and on and on, repeated again and again throughout the cosmos. No matter what, the Higgs boson did its job. The weak and electromagnetic forces would never be twinned again. The rest of physics would proceed, regardless of where in the universe that physics occurred. But where those regions met, cracks appeared in space-time itself. Topological defects, flaws in the foundation of the universe. These would be places where the cosmos could not reconcile with itself, with the Higgs boson reaching different states on opposite sides of the fault line. Kibble named them cosmic strings, and they were perhaps the most exotic object that the universe has ever produced, before or since. They would have finite width, no more than a proton, probably less, but definite spatial extent. They would be objects of intense trapped energies, energies that manifested as a mass, and they would also be incredibly long, stretching from one end of the universe to the other, growing along with the expansion of the cosmos. And finally, Kibble realized that they would not be mere features that would simply appear in space. Unlike the cracks inside an ice cube or the boundaries between domains of a magnet, these cosmic strings were alive. They would vibrate, curl, loop, and dramatically interact with the rest of the universe in curious, powerful, and violent ways. Kibble had unleashed something new, a lost ancient creature, one from distant days of eras long past, one that could only be fashioned in the exotic cauldron of a newborn universe, one that had the power to create and to destroy. The cosmic string is unlike anything in the entire universe because the modern universe is not capable of producing them. They could only be made once, when the universe was less than a second old. Indeed, Kibble found that most of them probably died, dissolving in flashes of furious energies. But some of them may have survived, even to the present day, and to encounter one would be to come face to face with the oldest creature in the universe. The Balrog is a survivor from the legends of the First Age. Primeval spirits of destroying fire, chief servants of the primeval dark power. They were supposed to have all been destroyed, but it is here found that one had escaped. In J.R.R. Tolkien's hugely popular The Lord of the Rings, published in 1954, the heroes of the book encounter a monstrous creature deep underground, a creature that has survived from before the world. This creature is known as a Balrog, and within the mythology of the series, they are monstrous relics from an age long before, with some surviving to the modern day, buried away in the depths, hidden from view. Yet within the narrative of the book, the greed of the dwarves leads them to dig deep into the earth in search of gold, and they reawaken this ancient threat. And so as with Tolkien's cautionary tale, perhaps we too have dug too deep in search of answers, unearthing our own cosmic Balrogs. $13.8 billion years ago, in the fires of the Big Bang, atoms formed out of the mist. From the primordial blast of energy, quarks appeared and then shaped themselves into protons and neutrons. After roughly a minute of existence, these protons and neutrons found each other and formed the first atomic nuclei. And roughly 380,000 years later, electrons were free to join. But of course, there were also other particles too, a whole zoo of them. Different types of quarks not included in the atoms, 3 types of neutrino, the muon and tau lepton, and dark matter. And all of that went on to form all of what we see, the stars, planets, galaxies and nebulae that dot the heavens. But that was not the only zoo that was formed in the fires of creation. For there was a second one, an even older one that ruled in the first instances of reality, less numerous but no less powerful, formed from the very architecture of the universe. And so let us begin to understand this menagerie of monsters by exploring cosmic strings. A single cosmic string would be no wider than a proton, and probably orders of magnitude thinner, and yet it would stretch longer than a galaxy. Indeed, in some cases, the strings may reach from one end of the observable universe to the other, a single unbroken strand of pure energy reaching tens of billions of light years in length. And this is possible because a cosmic string isn't really made of anything, the same way that a fold in a piece of paper isn't made of anything. They are just both objects of topology, defects. Their interior regions may be pure vacuum, or they may contain the state of the universe as it was before the weak and electromagnetic forces split apart. In other words, cosmic strings may contain the conditions of reality that we can recreate with our most powerful colliders, but stuck in their ancient state, as if frozen in place. A perfectly straight length of cosmic string will exert no gravitational influence on its surroundings. You will never be pushed from a cosmic string, nor pulled towards it. But you will see it. We do not yet know exactly how a cosmic string might interact with the rest of the particles and forces of the universe. It might glow brightly, a constant outpour of X-ray and gamma radiation. It might create a shower of exotic particles on its outer surface, exotic particles that then quickly decay into cascades of fast-moving electrons and neutrinos. But even if the string itself is silent, if this defect from another age is content to lay dormant and not reveal its secrets to the wider universe, it can't help but move. This is because a cosmic string has no matter to call its own. It's not made of particles or concentrated radiation. It's not built from anything. It only exists as a flaw, but still it holds together as the rest of the universe is always trying to repair that defect and restore the normal functioning of the cosmos throughout space and time. This gives cosmic strings tension, enormous tension, and since tension is a form of energy and energy is a form of mass, then the strings have incredible weight. The exact number depends on the type of theoretical physics you use to build a cosmic string, but in typical models, a single centimeter of string weighs more than 10 to the power of 16 tons. That means 1 kilometer of cosmic string outweighs the entire Earth. A cosmic string 1 billion light-years long would weigh 1,000 trillion solar masses, dwarfing even the heaviest galaxy cluster. And all that mass, without any gravitational influence at all, it wouldn't draw anything towards it. In fact, if the string doesn't otherwise glow or emit particles, then you'll have little evidence for its existence. Except for one trick. If you happen to travel around a cosmic string, returning to the precise position of where you started, you will find that you have not traveled a complete circle. Because strings are defects in space-time, they act as a wrinkle, distorting the topology of their surroundings. And so circles around them do not add all the way up to 360 degrees. Although if the string is in motion, then it has other ways of making its presence known. Ripples and vibrations travel up and down the length of the strings at the speed of light. Sometimes kinks will appear, which flash away in a storm of energies. Sometimes the strings tangle themselves up in loops and knots, and when they cross, the strings pinch off, dividing into two. Closed loops of strings vibrate with resonant frequencies, and with nowhere else to go, they emit enormously strong gravitational waves. Indeed, if the conditions are right, they may also explode as powerfully as a supernova blast, releasing this energy in the form of familiar, high-energy particles and radiation. However, we do not yet know if this process of tangling and vibrating itself to death leads to a cascade that infects the entire cosmic string. Such back-reaction calculations are too difficult to lead to solid conclusions. We don't even know how destructive they might be, although we do know that due to their density and tension, they could easily slice through the Earth like a hot knife through butter. But most importantly of all, we just don't know if cosmic strings, produced in the chaotic fires of the primordial universe, could have survived to the present day. Yet even if they have not lasted to our time, they are not predicted to be the only children of the phase transitions that rocked the early universe. There might be a small zoo of bizarre space-time defects out there for us to encounter. Cosmic strings are essentially one-dimensional. They have finite width, less than a proton or so, but stretch for up to tens of billions of light-years. They're caused when multiple domains of phase transitions meet together and cannot reconcile their low-energy states. But that's not the only way for these domains to meet. For alongside the cosmic strings, there were other, even more exotic creations. Two-dimensional walls that stretched and vibrated with their enormous tensions. Thankfully though, most of these disappeared quickly, as they couldn't hold themselves together in the face of cosmic expansion. Although some proposals have surfaced that cosmic inflation could have stretched these brains to become big enough to span the universe and remain stable. And then there were the zero-dimensional defects. The punctures, the holes, the places where tension wrapped itself up into a singular point. These were the monopoles. In 1931, Paul Dirac, one of the founding fathers of quantum mechanics, made a simple and unexpected realization. He saw that just like anything else in the universe, electric charge must be quantized. And this meant that all charges in the universe were some multiple of a single fundamental quantity, meaning that at least one magnetic monopole must inhabit the universe. We know that electricity and magnetism are really two sides of the same coin. They are mirrors of each other, but there is one way that this mirror is not perfect. Electric charge comes in two varieties, positive and negative, and magnetic poles also come in two flavors, north and south. But positive and negative charges can exist independently of each other. You can separate them, isolate them, and combine them as you please. But if you take a magnet with north and south poles and chop it in half, you don't get separated north and south poles. Instead, you get two mini-magnets, each with their own pair of poles. But the early universe did not follow the rules of the modern one. The exotic physics and chaotic phase transitions may have generated enormous numbers of particles that could carry singular magnetic poles. Particles with isolated north or south. Monopoles became such a generic prediction of theories of the early universe that they actually became a problem. There were none to be found. And so in 1980, it was Alan Guth who figured out a way to slay these ancient beasts. He came up with the entire concept of inflation, of the very early universe undergoing a process of rapid, uncontrolled, exponential expansion with the express purpose of making the cosmos so large that the monopoles, once prolific, would be so diluted so as to render them essentially undetectable. But were we to find one, a monopole would cause chaos. They're predicted to be huge, up to hundreds of times more massive than any of the familiar particles of the standard model, and their strong magnetic charge would disrupt normal matter by ripping electrons out of atoms as they passed. Although they wouldn't stick around for long, they could be easily accelerated by even weak magnetic fields, quickly reaching velocities approaching the speed of light. And finally, there was one more gremlin born in the flames of the nascent cosmos. In 1976, at the same time that Tom Kibble was digging too deep into our cosmic past, Stephen Hawking took his own glimpse into the fires of the Big Bang. But his objects of interest were much smaller than cosmic strings, though they were far more numerous. We know of only one way to make black holes in the modern universe, and that's through the death of a massive star. That's the only way to reach the pressures, densities, and gravitational might needed to compress a lump of matter below its Schwarzschild limit. But that's just the modern universe, with its relatively calm rules and laws. The early universe might have been so chaotic, so turbulent, and so energetic that black holes may have spontaneously appeared as local energies reached a catastrophic crescendo, collapsing entire regions of space-time into singularities. The modern universe cannot make a black hole smaller than a few solar masses, but these primordial black holes could have had masses as small as an asteroid. And, as with cosmic strings, they would not be content with sitting in the background. They emit radiation, ever so slightly due to a complex interaction between their event horizons and the quantum fields that soak through space-time. This radiation causes them to shrink and eventually disappear altogether. And the smaller the black hole, the more it radiates. That means that these primordial black holes would have been small enough that their lifetimes may be equivalent to the present age of the universe. In other words, they should be exploding right now. Hawking proposed this idea as a new avenue to discovering black holes, as their evaporation should register as explosions dotting the sky, and so we watch and wait to see if we can catch a glimpse of the deaths of these ancient creatures. Cosmic strings, domain walls, magnetic monopoles, and primeval black holes. Ancient monsters that push the limits of our understanding of physics. And yet physical proof has been practically non-existent for all four. For now, the Spacetime Zoo is firmly theoretical. Although arguably most of all, cosmic strings have the highest probability of being found. And indeed, were they to be found in the way that we hope, their discovery would have huge ramifications for our understanding of how the universe works. A theory of everything. Sometimes space-time creates phantom clones. First predicted by Einstein in 1912, and even hinted at by Isaac Newton 250 years before, gravitational lensing is what happens when light bends around the gravity well of a particularly massive object on its way to our telescopes. This distortion can lead to beautiful oddities in the sky. Galaxies bent like liquid around other galaxies, distant objects seemingly quadrupled, collections of stars stretched thin like spaghetti. And in 1979, a team of astronomers at Kitt Peak National Observatory in Arizona found one of the first gravitationally lensed objects, the distant quasar QSO 0967-561. The quasar consisted of two nearby components with extremely similar features. Immediately it was clear the two components were really two images of the same quasar, with its light getting split into different paths by an intervening massive object. Indeed, the difference was substantial. Light from one of the components arrived at the Earth about 14 months later than the other. And yet, there was a problem, for there was no nearby galaxy massive enough to explain that large of a separation. So what else could it be? Speculation began. Was this the sign of a cosmic string wandering between us and the quasar? A single floating cosmic string could make its presence known through its gravitational distortion. While it has no gravitational push or pull, it still bends space-time around it. And so if you were to look at a distant star or galaxy, and a cosmic string was sitting between you and the target, the light from the distant object would get split. Two paths of photons wrapping around either side of the string. And so some physicists speculate that this is what is happening with QSO 0967-561, but to date have failed to turn up any additional evidence. Though that is not the only method experimentalists have explored that uses Einstein as a guide. In 1916, Einstein also proposed the idea of gravitational waves, ripples in space-time that would be caused by massive gravitational events. As with their cosmic cousin, gravitational lensing, gravitational waves would not be detected experimentally until many decades later, coming from a black hole merger spotted by the hypersensitive lasers of the LIGO telescope. And yet we don't always need to create supersensitive machines to detect these ripples in space-time. Sometimes the universe offers its own measurement devices. Pulsars are the husks of dead stars, and they produce beams of radiation from their north and south poles. They also spin at a remarkably consistent rate. We detect them on Earth like a pulsing lighthouse as their beams wash over us. And in 2023, the International Nanograv experiment released its 15-year dataset of the timing of 67 pulsars across the sky, revealing variation in the regularity of their spins. And using this, the astronomers were able to provide strong evidence of a gravitational wave background across the universe, ripples in space-time itself that had affected very slightly the speed of the rhythm of the pulsars when they arrived to Earth. Like a ship taking longer to arrive in rough seas, the speed of the light received from the pulsars had been very slightly altered by the gravitational peaks and troughs. There are many proposed sources of this sloshing background of gravitational waves, and cosmic strings are one possibility, although arguably not the forerunner. Indeed, there are papers speculating it could be domain walls or simply more black hole mergers. And so the hunt for a definitive signal goes on. To quote cosmologist Eugene Lim, "If we discover cosmic strings, it'll be the result of the century." But to quote Carl Sagan, "Extraordinary claims require extraordinary evidence, and right now, the evidence is a bit thin." Indeed, it is true that no cosmic strings have ever been found conclusively, despite decades of tantalizing evidence. They certainly don't exist in abundance, otherwise they would have shown up in the cosmic microwave background and in the cosmic web. But we also still haven't been able to rule them out. And so, how else could we search for them? Perhaps, some believe, the greatest living physicist may hold the answer. In 1990, chit-chatting between sessions at a physics conference, I asked attendees who is the smartest physicist of them all. Several names kept coming up, but mentioned most was Witten. He is often likened to Einstein, but one admirer reached even further back for a comparison, suggesting that Witten possesses the greatest mathematical mind since Newton. Ask any physicist about Ed Witten, and you'll immediately see the cult-like devotion he has earned. Stories about him echo through the halls of academia, and quotes at 10 a penny, even from legends themselves. Roger Penrose says of him in his book, "Where Witten goes, it does not take long for the others to follow." He picked up mathematics at an early age, like many scientists, but unlike many scientists, he became so bored with it that he pursued other endeavors. In the end, he became a history major and dabbled in politics. And so it was only in 1973 that he entered graduate school at Princeton in their applied mathematics program. And then, somehow, nobody's exactly sure how, this history major ended up working with David Gross, a giant in his own right who would go on to win a Nobel Prize in physics. From there, Witten began to work. Indeed, his genius, even amongst fellow geniuses, was unparalleled. It is said that Gross would give him an assignment, expecting it to take months, only to have a solution returned to him the next day. His colleagues would spend years becoming experts in their domain, only to become second place in less than a week when Witten learned of the idea. "We know a lot of things," he once said, "but what we don't know is a lot more." And so naturally, when Witten first encountered the concept of cosmic strings in the 1980s, he saw nothing to fear. Instead, he saw opportunity. For when Witten first learnt about strings, he didn't think of them as cosmos-defying forces of ancient physics. Instead, for him, they were much, much smaller. It was in the 1980s that physicists realized that string theory was a candidate for a theory of everything, that there was a slim possibility that all forces of nature and the entire zoo of fundamental particles could be explained by tiny, vibrating strings. These strings were small, no bigger than the Planck length, but they vibrated at different frequencies, with each frequency corresponding to a different kind of particle or force. But the strings of string theory were hopelessly out of reach of both theory and experiment. No mathematical tool could make firm predictions as to how the strings manifested into the multitude of particles in the universe. And no particle collider, no matter how powerful, could ever reach the energies necessary to directly probe the scale at which the strings exist, bar one that spanned the entire length of the solar system and beyond. So how could we study something that was too small to ever be seen? Witten realized that the universe may be able to do it for us. He was the first to realize that there might be a surprising connection between the cosmic strings of phase transitions in the early universe and the superstrings of his beloved string theory. And that connection was inflation. The splitting of the forces just after the Big Bang didn't only usher in a phase transition, it may have also led to an explosion in expansion. Indeed, if the theory of inflation is true, in less than a nanosecond, the entire universe expanded to over 10 to the power of 62 times its original size. And in that inflating universe, everything got bigger. The subatomic became macroscopic. Extremely minute variations in space-time would stretch to become the seeds of gravity that would allow structure to grow. And in this chaos, Witten realized that Planck-length superstrings might be able to become cosmic superstrings, blown up countless trillions of times in size. And so if we were able to find a cosmic superstring, a macroscopic manifestation of the theoretical underpinnings of reality written across the sky, it would provide an unprecedented view into our most difficult physical theories. We do not know how to proceed in string theory, as the calculations have proven to be too complex. But if we had direct experimental access to one, we could train our observatories on it and learn its secrets. Cosmic superstrings would still be flaws in space-time, but of a slightly different character to regular cosmic strings. Although Witten's calculations showed that most of them would evaporate away shortly after inflation. But he also found that some might get stuck. String theory predicts that there is more to the universe than our usual 4 dimensions of space-time. For the theory's maths to work, it requires additional spatial dimensions. But the universe we experience is obviously not extra-dimensional, so these extra dimensions have to be tiny, curled up on themselves all the way down to the Planck scale. And this means that when inflation stretches out superstrings, some of them may get caught in those extra dimensions, wrapped around and around at microscopic scales like tangles in a fishing line, thus preventing them from collapsing in on themselves in a burst of radiation. This would allow them to persist and survive as macroscopic and cosmological objects, where they might go on to wreak havoc. And so Ed Witten was not afraid of these ancient monsters from the deep past of the universe. He hoped that we could see one in real life and transform his theoretical mathematics into practical physics. But how exactly does one go about hunting cosmic strings or cosmic superstrings? Well, for decades, cosmologists thought their influence might be written on the stars themselves. In the chaos and turbulence of the infant universe, the phase transitions that split the forces didn't just create one cosmic string. They would have created thousands of them, as the cosmos split and fractured into domains of distinct low-energy states, with these strings separating each one. This should have formed a colossal string network that would have spanned the entire volume of the observable universe, which at the time was no larger than a few centimeters across. And from there, the expansion of the universe would have done its work. Since strings are entities of space-time, they would stretch along with expansion, and so as the universe got bigger, so would the strings and its network. And some physicists speculate that that string network may have provided the backbone to the universe. In the 1980s, cosmologists were struggling with 2 seemingly contradictory observations of the large-scale universe. For years, they had recognized that galaxies were not scattered around randomly, but traced out dense clumps and thin filaments, leaving vast, empty regions behind. Some observations suggested that the universe was made of meatballs, large clumps of superclusters of galaxies with nothing in between. Other models hinted at the existence of vast, broad walls of galaxies, giving the universe a honeycomb-like structure. But the cosmologist J. Richard Gott offered a compromise. Why not both? He proposed a cosmic sponge, which featured both dense clumps, the meatballs, and the broad walls, the honeycomb. But this insight introduced its own troubling question. The universe of today is large and largely homogeneous. It is relatively the same from place to place. And so how do you build a cosmic sponge, today known as the cosmic web? How can you convince galaxies to group together to form gigantic universe-spanning patterns on top of a homogeneous background? The string network was an intriguing suggestion. In this idea, the cosmic strings would have twisted and braided together, tying themselves into knots as they spanned the breadth of the cosmos. It seemed the perfect solution to the cosmic web, providing a gravitational anchor for matter to accumulate and build larger structures. And as well as this, if the cosmic strings were responsible for building the greatest structures in the universe, then they would also leave behind another trace of their existence, even if they did eventually vanish from the cosmic scene. They should have influenced the appearance of the cosmic microwave background, the oldest light in the universe, left over from when it was only 380,000 years old. And so, on November the 18th, 1989, John Mather and George Smoot watched as a Delta rocket launched their brainchild into orbit. It was supposed to launch aboard a space shuttle, but the Challenger disaster of 1986 forced them to change plans. The satellite was COBE, the Cosmic Background Explorer, and its purpose was to create the most detailed map of the cosmic microwave background ever made. Mather and Smoot would go on to win the Nobel Prize for their efforts, because COBE was indeed able to paint an exquisite portrait of the young universe, providing cosmologists with their first high-res image of that era. That image is of some of the earliest seeds of structure to appear in the cosmos, with tiny 1 part in 100,000 differences in temperature representing what would someday grow to become galaxies and clusters. And the pattern of those temperature differences, their sizes and scales, tells us what the early cosmos was doing to plant those seeds. Cosmic strings should have a very unique fingerprint that would show up in these splotches in the sky. Not a single hint of them was found. To quote Brian Greene, "Nothing to me would be more poetic, no outcome would be more graceful than for us to confirm our theories of the ultra-microscopic makeup of space-time and matter by turning our giant telescopes skyward and gazing at the stars." For cosmic strings, that day has yet to come. But that is not the end of the secrets they hold. For at the same time the COBE rocket was soaring into the sky in 1989, a rebellious physicist was making his own calculations. J. Richard Gott liked to gamble, but not at the poker table or the roulette wheel. He liked to wager about the future. In 1989, Gott was standing at the Berlin Wall, the infamous dividing line that bisected the city. He wondered how much longer it might last. And so to solve this riddle, he applied not a theory of geopolitics to the question, but a cosmological one. One of the most important foundational assumptions in cosmology is known as the Copernican principle. It states that humanity does not occupy a privileged or special position in the universe. Gott was standing at the wall in 1989. He assumed that he didn't occupy a special position in space or time, that the fact of the wall's existence when he happened to be visiting it was not unique. At the time, the wall had stood for 28 years, and using this as a guiding principle, he calculated the bounds of the probability of the wall remaining standing into the future, arriving at a 95% probability that the wall would last between 1/39th and 39 times its present age. In other words, it would last somewhere between 8 months and 1,092 years. It fell just a few months later. Years later, Gott even applied the same formulation to estimate the future longevity of human civilization. Based on the Copernican principle, he calculated that humanity would exist for somewhere between another 100 years and 400,000 years. But just a short while after his visit to the Berlin Wall, Gott made a different kind of wager. This one had nothing to do with political boundaries or even the fate of the universe. It was about time travel. In 1991, God made a claim that he could travel back in time, and all he would need? A pair of cosmic strings. Time machines have always caused problems in physics. Our modern language of space and time comes from Einstein's general theory of relativity. Matter and energy tell space-time how to bend, and the bending of space-time tells matter and energy how to behave. But relativity itself doesn't care about which direction in time objects travel in. The future is the same as the past when it comes to matters of gravity. And so all it takes, at least according to general relativity, is to find special structures, patterns, or movements that allow one to travel back in time. In the parlance of relativity, these are known as closed time-like curves, paths that never exceed the speed of light, always putting one step in front of the other, but manage to loop back on themselves and return to their own past. One of the first people to find a closed time-like curve in Einstein's maths was Kurt Gödel, who used it to taunt Einstein. If relativity admitted time travel into the past, then perhaps it wasn't as great and powerful as everybody thought. Einstein had no response. But Gödel's time travel required a universe that was rotating, and the universe did not seem to be rotating. And so in 1991, it was God who found another time travel machine in Einstein's theory, one that did not require a rotating universe. God found that if you take two cosmic strings of infinite length, bring them close enough together, then separate them at nearly the speed of light, a sort of tunnel in space-time would open between them. Since cosmic strings are topological defects that manifest as flaws in space-time, the two separating strings would work to essentially tear space-time apart between them. And if you were to fly a spaceship down the length of the string, again traveling at nearly the speed of light, if you followed a particular path, you would wind up in your own past. But of course, time travel into the past is supposed to be forbidden. If we found a cosmic string, therefore, this might open up a crack in theoretical physics that we could not repair. And so luckily, to this day, no cosmic strings have ever been found, or the domain walls, or the monopoles. We have no signals, no fragments, no artifacts from the earliest moments of the Big Bang. We have searched the cosmos in vain. But they should exist. Indeed, the fractured state of the early universe presents us one of the greatest unsolved puzzles in modern physics. The hot Big Bang should have made monsters in abundance, and yet there are none. The cosmic strings should have built the cosmic web. The monopoles should have darted here and there. The primordial black holes should have wreaked havoc. And yet, it's quiet out there. Too quiet. Of course, this may come as a relief. God's time machine requires the existence of the cosmic strings, and time travel into the past opens up innumerable headaches, paradoxes, and violations of basic assumptions of reality like causality. No cosmic strings means that this chaos can stay contained as nothing more than a provocative thought experiment. And so, all we can do is wait and wonder. And if we're lucky, or perhaps unlucky, then one of these creatures forged in the fire of the Big Bang itself may arrive on our cosmic doorstep. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave us a comment to tell us what you think. Thanks for watching, and we'll see you next time.